In this video, we'll be demonstrating how you can interpret the results generated by TADMaster to find the similarities and differences between TADs identified from multiple different TAD callers. In this particular case, we are using a results page generated by TADMaster Plus. However, if you use TADMaster or TADMaster Plus, the results page will be the same, with the slight difference being the select normalization. As a result, we show the normalization selected as well as the raw contact matrix that you provided. Beneath the normalization, there's a TAD heat map region. You can access that by simply selecting this button here. And further below are the various different results provided. As you can see here, we've provided multiple different TAD callers. You can select between all the various TAD callers to view the results by simply checking the checkboxes, and then you get the graph following. But before we start interpreting these results, let's take a look at the heat map. This is the TAD heat map page. As you can see, the select normalizations are still available, and we provide a note that depending on the size of your contact matrix, the load times can vary. Here I've preloaded two separate methods, and you can see a square heat map provided here. Currently it's in log form. If we want to view it in raw form, which is the format that you provide, we can do that by simply selecting raw. This is the raw view of the contact matrix provided, and as you can see, it's a very sparse contact matrix. If you zoom in, there is contrast here. However, visually it's hard to see what the methods are identifying. That's why we also have a log scaled view, which was shown originally, which we'll switch back to. The log view provides a more in-depth visualization of the various perturbations that are happening in the results. So by default, the log view is selected. However, both options are available for analysis. So to take a closer look at what's going on in the contact matrix, we can highlight in and view the different TADs. And of course, you can select any number of TADs that you wish to view. So for this example, let's select one more, and it will take a second to load in. Right, we had loaded in one more method, cluster TAD, and as you can see quite clearly from the color difference from cluster TAD, that it's identifying much larger regions than the other two selected methods. So again, we can highlight in, view region, and visually it's apparent the differences in the TADs identified by these methods. However, we provide much more in-depth analysis of this, and to view that, we need to go back to the main result page. Below the TAD heat map button, our first graph is the number of TADs, which is, as the name describes, simply the count of the number of TADs that each method provides. Hovering the mouse over each method will give a count of the number of TADs identified by that method. And as you can see in this result, there's a wide range of diversity in the number of TADs identified. Of course, that alone does not provide a clear metric of comparison for the methods, because some methods can be finding smaller sub-TADs, while other methods can be finding larger TAD regions. To get to this point, we also provide the size of TADs, and I'll quickly select all the methods. This graph gives the size of TADs in multiple points of comparison based on the resolution you provide. So the y-axis of this graph is in the genomic bins. So it's dependent on the contact matrix that was provided, as well as the resolution. As you can see here, the graph is kind of squished because one of the methods has a very high outlier compared to the majority of the results. So to get a clearer picture, let's deselect that method, and it reloads. And you can see the size comparison between each of the methods. Typically, you can expect that methods that have a low count of the TADs identified will conversely have a larger TAD size. And you can see that in both cluster TAD and GMAP. Both the size of the TADs identified and the number start to paint the picture of which methods might be similar and which methods might be worth further analysis with the heat map or further analysis by any of the metrics that we provide below. The next point of comparison that we provide is the number of shared boundaries. This graph compares the start and the end of the TAD identified regions for all methods compared to the selected method. On the y-axis, it gives a simple count of the number of boundaries that were shared between each method. On the x-axis, we have tolerance, which is given in terms of the resolution provided. So at a 0 tolerance, it requires an exact match, and at a 1 tolerance, we require the match of the boundary to be within 1 genomic bin of the data provided. As tolerance increases, the number of shared boundaries also increases. However, it does start to paint a picture of which methods are in higher concordance. Beneath this graph, we compare similar metrics where we looked at the stacked shared boundaries. In the graph below, we provide a similar metric of comparison presented in a more condensed manner, where it's an all versus all comparison. This is looking at the boundaries of each method compared to all the other methods. So in this example, we have a tolerance of 1. So you can look at the method selected previously, cluster TAD, and see how many boundaries were uniquely identified or identified by any other method within a tolerance of 1. Cluster TAD has identified 33.87% unique boundaries. This is in comparison to a method such as Armatus, which has detected no unique boundaries. So that means that all its boundaries were also identified by at least one other method. Similarly, beneath this graph, we have stacked shared domains. So this compares both boundaries. So for something to be considered a shared domain, both the start and the end of the TAD must be identical between methods. So we can look at a method such as cluster TAD or GMAP, see that the majority of the domains identified by these callers were unique to these methods. The next graph that we will look at gives an overview of the amount of domain overlap between the methods. So this graph provides a comparison of the identified area that each caller has identified as a TAD, and it compares that to the other methods. This is why you can see with HiC-Seg selected, it has a measure of concordance of 1, because all the area identified by HiC-Seg is also identified by HiC-Seg. So that's not as interesting as looking at, let's say, a comparison to GMAP, where the area identified by HiC-Seg, only 39.9% of that was identified by GMAP, and conversely for all the other methods provided. The importance of a measure of concordance is it disregards issues that might arise from strictly looking at domains or boundaries, because some methods and approaches find smaller sub-TADs. So it's important to have a good comparison between methods that doesn't strictly rely on boundaries and domains, because if one method is identifying larger TADs and another one is identifying smaller sub-TADs, but they're both identifying the same area, that's important. And to kind of help encapsulate all the information that's provided in all these separate graphs, we have the comparison of the average measure of concordance. So this is a one versus all approach. So it takes the value that each method has in comparison to all the other metrics. So this will give a good idea of how similar the results of one method is versus all the other. So in this case, the catch 0.65 has the highest level of concordance, which means that its TADs identified were most commonly also identified by all the other methods. And this is shortly followed by spectral and top DOM to kind of help give a good overview of the information that we've shown thus far. We also provide two clustering methods. The first one being TSNE, which is provided with two initial embeddings, the first one being PCA, the second one being randomly, and we'll come back to these graphs very shortly. The final clustering is a Pca comparison, and you can see the results down below. So if we take a closer look at the clustering data, we can see that there is a cluster of 4 methods that seem to be tightly packed. And if we look at that spectral, top DOM, catch, and the other catch, which were also the methods that had the highest average measure of concordance. So there's a cluster here, and it looks like the same methods are clustered down here. And then finally in the PCA clustering, those same 4 methods are clustered together. So we can expect, just taking a brief look at this, that we are going to find high number of shared boundaries, high levels of concordance between these methods, and that these methods are identifying similar regions. Whereas methods such as Armitage and cluster TAD, who are farther on the outskirt of the main cluster, are likely identifying regions that are unique to the respective method.